visual system and visual motor transformations. And I'm really going to focus, I know Dr. Chadner talked a bit about higher level processing of saccades, I would guess, in his lectures, and voluntary movements. And I'm going to focus on some work, actually, which has its origin at Hopkins. I'll talk a little bit about Dave Robinson, one of the founding fathers of the biomedical engineering department at Hopkins, in the middle of my lecture. I talk about eye movements and why there's such a nice model system for really understanding motor control. So, as we all appreciate, one of the main functions of the brain is to monitor sensory information and use that to guide motor commands so we can interact with our world. And everything that we do every day that requires the integration of information across multiple modalities in order to, pick up a cup of coffee, you have to see it, you have to shape your hand, you have to feedback from your proprioceptors and your somatosensory endings in your hand to complete the grasp properly. So everything we do is really ultimately a sensory motor transformation. We're taking sensory information, integrating it to basically generate accurate and useful motor commands. And when I gave my first lecture, I used this as an example of how we really use many parts of our brain in order to do the things that we do every day. So I said, if you think about a tennis shot, there's a lot of planning that goes into it. There's motivation. So there are areas that are just involved in getting you to where you need to be and anticipating a movement. And then there's also the programming, sort of the nuts and bolts of how do you program the proper movement? How do you activate the muscles in your arm to get that proper swing? How do you calibrate those circuits? And there's no real clean divide between these areas. I think what we've discovered actually is pretty interesting. Is if you look at what are people consider primary sensory areas, so for example, visual cortex, primary V1 cortex, which gets direct thalamic input, we actually are learning more and more about motor signals that shape sensory processing very early on. So this idea of sensory motor integration, multimodal integration is a really very important area of study in neuroscience right now. And one of the nice things about the tools that you've developed in a curriculum like the DME curriculum here and more quantitative curriculum is you have ways to actually build models about what the brain might want to do with this information, test it, and develop really sort of concrete frameworks to understand how the brain is doing what it does. So what I'm going to show you is a really, I think, particularly nice example of where there's been this nice fusion between physiology, neuroscience, and quantitative engineering approaches to understand pretty simple visual motor transformation. So the question we're going to address in this lecture is the question of how does the brain generate appropriate motor commands to move the eye, the axis of gaze, to look, for example, from one of your friends to the other side of the room. How does the brain do that? And what can we learn about different nuclei and neurons within those nuclei and their behavioral firing rate patterns to understand how we accomplish this pretty simple task? So the first question is, why study eye movements? Why not study arm movements? And I think you probably learned a little bit about arm movements already, but arm movements are complicated, and very often when people study arm movements, they limit the arm movement to one dimension, right? Because otherwise you have changing inertia, so as you move your arm closer or further from your body, the whole dynamics of the effector, your arm changed. And we don't have to worry about this with the eye, right? The eye actually rotates around an axis in your orbit. There are no joints in the system. Its inertia, I'll show you later, is negligible, so that simplifies the math. And many of you may not know this, but your eye actually is moved by your brain using 6 different muscles. And if we limit our eye movements to just horizontal, looking left and right, that really reduces the problem to just 2 muscles. So that's a pretty simple behavior to model. So just for comparison, if you think about moving your head back and forth, there are 40 neck muscles involved in moving your head back and forth. So that problem's a lot higher dimensionality, a lot of redundancy, and how you can solve the problem. So arm movements have been a great model system for understanding sort of biomechanical models of how the brain generates accurate behavior. If you think about eye movements, as a lot of neuroscientists and engineers have thought, typically they're broken into 2 two primary classes. You have voluntary eye movements. I think people have already learned a little bit about saccadic eye movements, right? The quick eye movements you make to look from one side of the other. Pursuit eye movements that you make to track smoothly moving targets. So if you're trying to read a textbook, right, you can't make smooth eye movements because there's no smooth target motion. You'll make little jumping saccade eye movements. You need, if you're watching a tennis match and the tennis ball going back and forth, you can watch that tennis ball and you make these smooth pursuit eye movements. And then there are also vergence eye movements. And vergence eye movements are, if I look out here and then I look down at my computer, my two eyes are going to be moving sort of in different directions, opposite directions. So whenever the eye movements are not conjugate, that means not moving like windshield wipers together, that's called a vergence eye movement. So it's really the difference between the two eyes. And we're learning over time how vergence commands are integrated with the other systems that generate smooth pursuit and saccadic eye movements. So I'm going to focus primarily on saccades today. I'll talk a little bit about pursuit because we need it to try to understand how neurons are encoding information. And then on Wednesday, I'm going to talk about another class of eye movement called the vestibular ocular reflex. And we have eye movements whose job is to help us keep the world stable on a retina. So voluntary eye movements help us redirect our gaze, axis of gaze purposefully, whereas these reflex eye movements are really there to help us keep a stable world on our retina as we move through and to keep gaze stable. So they have different goals, redirection versus stability. So I'll talk more about the vestibular ocular reflex and optokinetic responses on Wednesday. All right, so this just shows examples of what I mentioned, saccades. Typically, you can look at any eye movement in terms of its position, how much the eye is rotating. And let's say, for example, these are horizontal eye movements. So you're looking at, let's say, down is to the left and up is to the right. Right? So we have a rightward saccade. And what you can see here, and the head's not moving in this case, and then this would be eye velocity. So you have this sort of step change as you move your eye from here to here, it stays, and during that change you have a velocity, right? So this is the same saccade just looked at in two different ways. And for pursuit, you'd be tracking a moving target, so you can see the position would ramp up and you'd have this eye velocity signal that would be your pursuit signal that would be consistent with whatever your target velocity is. These are both shown in position here, and then this would be the velocity view. And then vergence again would be two eyes moving different ways, right? The difference between their two motion is considered vergence. So when you make, it's a big question, if you're sitting here, you're going to say, well, I'm looking here, how do I decide to look over here? And that's like kind of a fundamental question that you could study in philosophy, right? Like, what's free will? How do I decide right now, at this point in time, I'm going to move my eyes from here to here? And what we do know is that there are some very salient aspects of visual stimuli that might help you more readily move your eyes to a target of interest. We also know that you can think about things. You can make something called anti-saccade, so you actually train yourself to move your eye in the opposite direction of a target of interest. You might want to do that if you're in the New York subway. You see somebody, you're going to keep your eyes the other way, right? They look a little dodgy, right? So we have a lot of cognitive control over the kinds of eye movements we make. So it's not surprising that if you look up in cortex, you'll find areas like frontal eye fields, supplementary eye fields, parietal cortex. These are areas in frontal cortex. These are areas out in parietal cortex that all come together to tell you where and how to look in space. The hub area is down here. It's called the superior colliculus. You guys, I think, already learned a little bit about the superior colliculus. No, not at all? Okay. All right. Reza changes his slides every year, so I'll tell you a little bit about the superior colliculus at the end of the next lecture. And the superior colliculus then projects down to the brainstem. So we're really just going to focus on the brainstem for today, right? Because there's a lot we can learn about how to approach a problem. I think this work is actually takes you through a very didactic way of approaching a scientific problem, and I think it's pretty profound when you think about the fact that people like Dave Robinson and others came up with this approach and maybe made so much progress in understanding how things work. I'm not sure if it's online already, but I have there's a chapter in a textbook that pretty much follows this lecture, so if you get confused, just go to the textbook. It should provide a lot of information. There's one chapter I pulled out that's relevant. Okay, so what I'm going to start on is just talking about, so I've broken the lecture into 3 parts. So the first is just understanding the extraocular muscles. How are they attached to the globe? What are their pulling directions? And the motor neurons that basically innervate them. And we'll talk about understanding how the motor neurons fire during saccadic eye movements, and then we're going to look at the implications of some biomechanical models and predictions that can be made. Okay. So if you look at the side of your eye, and if you could look at the side of your eye, what you would see is you have there's 6 muscles. From the side you can see there's 4. So you can see there's the lateral rectus, there's the inferior rectus, there's the superior rectus, there's the inferior oblique that kind of wraps itself around. There's also the superior oblique up here. And then what you can't see is one that would run along the nasal part of the orbit called the medial rectus. So 6 muscles per eye. Again, these 4 recti muscles. The recti muscles are pretty easy to understand. So if you pull on the lateral rectus, just think about its pulling direction. If you're pulling on the one that runs along the temporal part of your orbit, it would move your eye towards your ear. If you pull on the medial rectus, it would move your eyes towards your nose. The superior would move your eyes up, inferior down. And then these other 2 oblique muscles actually will tort the eye, so it twists around like this, in addition to lifting it up or down. And that's what's just shown here. These 6 muscles, between them, you have 3 dimensions of eye motion. You have horizontal, vertical, and a bit of torsion. So people probably don't realize that your eye does tort a bit. So what you can do actually is put somebody on an office chair, put their head up and spin them, and you can see the eye just kind of tort a little bit with their head and the axis of rotation. And when we make normal eye movements, depending on the position our eyes is centered from the center, we have different amounts of torsion. And that torsion is determined by something called Lisking's plane, for people who are interested in 3-dimensional eye movements. And there's been a lot of work trying to understand what constrains eye movements to this point. So how about the motor control? So how does that work? And I talked a little bit, I think, about the fact that we have cranial nerves, and that, for example, remember you have this, from the diencephalon, the thalamus, you have these optic cups that come out and form the retina. Okay, that's one of the cranial nerves. Basically, the optic nerve is one of the cranial nerves. So that's a sensory nerve, right? And if you're thinking about the auditory system or the vestibular system, there's also a cranial nerve that brings information in from the inner ear. That's the 8th nerve. So in addition to have sensory nerves, cranial nerves can also be motor. So they can do things like activate your facial musculature, but they can also activate your eye muscles. And there are actually 3 motor neuron pools, nuclei, in the brain, each of which has the axons of those motor neurons projecting out to the eye muscles, forming 3 different cranial nerves. Okay? And that's what's shown here in red. You have the 3rd nucleus here, the 4th nucleus, and then the 6th nucleus. So the 3rd nucleus is also called the oculomotor nucleus. The 4th is called the trochlear. You don't necessarily need to remember them. You can just call them 3rd and 4th. And the one we're going to talk about the most is the 6th nucleus, which is the abducens nucleus. And if you guys remember that basic brain survey we did very early in the class, right? This is the pons down here, the cerebellum on top. This is the mesencephalon, right? So this is the midbrain here. So all these structures sit deep in the brain, basically, in the mesencephalon and the pons, the rhombocephalon. Okay. So this is what I already told you. If we just focus on the areas that have motor neurons that project out to the eye muscles, we have 3 of them. And they actually send projections in very systematic ways. So the abducens sends projections just to the motor neurons that act, or has motor neurons that just project to the lateral rectus. Okay? So that actually makes it very easy from a neurophysiology point of view. You put the lecture there and just record from neurons that are controlling how the lateral rectus moves. In addition, the ocular motor nucleus has neurons from most of the other muscles, or projecting most of the other muscles, and then the trochlear is attached to the inferior oblique. Okay. So in general, I'm correcting this at the bottom, what's been really interesting is it looks like most motor neurons are It used to be all, but now it's been a little bit of a caveat. A given extraocular motor neuron, so a motor neuron, one of these three nuclei, participates in all classes of eye movement. So I showed you that table of 5 different types of eye movements. One motor neuron would contribute to all of those. It's not like you have separate channels for different kinds of eye movements. The one area that seems a little complex is vergence. So the idea is that maybe for slow vergence, there may be a ring of cells that are undersampled in each of these nuclei that are actually controlling very slow resettling or realignment of vergence after you make a movement from here to here. You have a dominant eye that gets to the new target right away. The other eye will slide over a little more slowly, and that movement may be controlled by these special ring motor neurons, but that's still under this investigation. Okay. So now I'm just going to talk about saccades and focus on saccades for a little bit. So again, saccades we make all the time. So you go to the store and you want to decide what kind of apples you want. So you look and see which look the fresh. You check the freshest. You check the prices. And when you're doing that, right, none of the apples are moving around. So what you're doing is you're scanning that visual scene, making holistic eye movements that are called saccades. Okay, and in between each of those saccades, you're going to fixate, right, and look at the apple. Look at the red apple, look at the Golden Delicious apple, look at the Granny Smith apple. So you basically have periods of fixation between these saccadic holistic eye movements. And you can only generate saccades so quickly. So it's hard to generate saccades without a fixation of 200 milliseconds or more. Right? So we generally can't just keep generating rapid-paced saccades. You have a set period of fixation before which you make your next saccade. Okay, so how do the motor neurons respond? And what we're going to do is start with a mechanical analysis and then talk about motor neuron firing rates. Again, this idea of scan paths. And reporting eye movements become very interesting. So anyone who does web design, small tracking cameras are so easy to get now. You can actually just look at the scan paths and see where people spend time when they're looking at images, and that actually is very important for understanding how to put what you want people to pay attention to in a place that makes it the most salient. And people are actually now developing models to try to predict how people will look at different types of media, which is interesting, right? Because we all think we have free will, but these models do have the ability to make probabilistic models of how we're going to scan certain types of images. This just makes the example of course faces. What's most interesting to us are eyes. So this is a really sort of intuitive example. So if you put a face in front of somebody, they will most likely look around the eyes, back and forth between the eyes, which you can see both in this bust of Nefertiti and in this picture of a woman. But you can do another game where you have a more complicated situation. You might say, guess how much, guess who's wealthy? And people will look at clothes, right, and shoes, right? Then you could say, guess how old people are. And so you can really direct, based on a cognitive context, how people scan pictures. Okay, so from an engineering point of view, what you can do is think of try to understand how the brain is controlling eye movements as basically a systems neuroscience or a system control problem. So what we have here is just a very simple system with an input X and an output Y. And the idea is that both of these signals are going to vary as a function of time. And as an engineer, your goal would be to design a system, right, S, that would result in some sort of relationship between X and Y. But as a neuroscientist, right, what you're actually doing is sort of the inverse of that. What you know is X, because you can measure X, and you can maybe measure Y, and then what you can try to do is understand what the system is. So here we're identifying, so it's a systems identification problem, trying to understand what the system actually is. So in our case, the question is, what is the input and what is the output? So the output obviously is going to be eye movement, right, because that's what the brain is generating. The input could be muscle tension. We could try to understand how the tension of the muscle is driving the eye movement, or we could measure, that's hard to measure, people have tried it, and tends to muck up how the eye's actually moving, not surprisingly, these are really tiny muscles. There's a group at UCLA that's tried to make very small measurement devices that didn't work very well. But you can measure the motor neuron drive and then infer from that the control and understand how the neuronal firing rate is actually driving the behavior. So again, the question is, what's the system? And one thing in the approach I'm going to describe is it assumes linearity, and I think most of you know what linearity is, but the idea, right, is you have some input x that results in an output y, and then another input x that results in another output y, and the idea is that you can then sum those two inputs and predict the output based on the summation of what you had for each input alone, right? And that's what's shown here. So if the system doesn't obey this basic principle of superposition, this type of approach is not valid. So this is just sort of a summary of the type of approach that we're going to go through now, which is a really basic mechanics-based approach. And I think this is really helpful because you can build these models and come up with dynamic equations that have kinematic variables. But it's really, I think it's helpful to think about what they mean and build an intuition for what they could actually represent in terms of the problem solving how the brain is programming eye movements. So again, to understand how you move your eye, we can first consider the example of mechanics relating the force to eye movement. So the idea is if you apply a force to a spring of a stiffness K and stretch it to a length L, right, then Hooke's law, which I think you guys probably all should know and remember, says that the force that you need to apply to keep that spring at that length would be proportional to this spring constant, right? So it's a very simple relationship. Force equals K times L. So then we can build another element, or look at another element. And here what we're going to do is apply a force not to a spring, but to a system that's characterized by pure viscosity with a coefficient R. So I always use the example of, think of a big hypodermic needle filled with water, and you try to push the piston at a constant velocity versus a big hypodermic needle filled with honey, right? So to keep it moving at the same velocity if it's honey, you're going to have to apply a sustained force that's higher than if it's filled with water, right? So the idea is if you push at a constant force, the plunger will move at a constant velocity dl dt, so just the derivative of L, right? So that force equals R times dl dt. So then what we can do is put these two elements together, these very simple elements together in parallel, and this is called the viscoelasticity. And what this is effectively is the most simple model of muscle that people can use, right? And the idea is that you have now force equals K times L, right, which is that spring component, the elastic component, and then R times dl dt. And this is effectively a first-order differential equation, right? So if our system was a viscoelasticity, solving this equation for a given input, right, motor neuron firing rate, for example, should produce the desired output. So you could think, well, what else might want to, if this is very simple, is there something else I should add to this analysis, right? Maybe I need to consider mass. Maybe mass is important. So the other thing we can do is add a mass to this system, right? So for Newton's laws of motion, we know that F equals ma, right? So A here is acceleration, so that's dl dt, the second derivative, right? So that's basically acceleration. We started with length, went to velocity, and now we're going to acceleration. And now if we added this all together, our system would now be described by this second order differential equation, right? Where we have this elasticity, this viscosity, and then this inertial term. So that's just intuition, right, for how these equations link to the actual physics of moving your eye, right? And I put this up because I think it's important. The terms I'm going to describe now were actually done by David Robinson. And I put this here to make you pause and ask you guys to think a little bit before I jump to these experiments. And how would you try to understand the biomechanics of your eye plane, right? What kind of command the motor neurons should be sending to actually move your eye in orbit. So, and this is what, so the idea, right, is you have your eyes sitting in your orbit. You've got to actually program the right forces to make it move around. To do that, you need to know what kind of maybe elasticities, right, viscosities, inertia you have to deal with, right, and overcome in order to move your eye. So it's basically a biomechanics problem. So how might you sort out what those biomechanics are? And this is what Dave Robinson did in a very elegant way. And he not only solved these sorts of more conceptual modeling problems, but then, as I'll show you, went back and actually did the neurophysiology to validate his predictions and make further predictions that were then even further validated. So it's a pretty spectacular case of being able to use models to drive experiments, validate those experiments, and then make further predictions. So again, just if we relate this kind of systems identification approach back to our problem of understanding how the brain's going to control eye movements, we have this input and the output, and we could say, well, maybe the system would be the second order differential equation. It seems like not a bad place to start. And okay, so what did Dave Robinson do? So he did a series of 3 tests, and he basically did these tests using sort of volunteers, probably DME students who wanted to do letters for med school, people like yourselves. This is, you may know this is back in 1964, so I'm not sure if you would be able to do this anymore. So what he did is he took a contact lens, and it's not not like the nice permeable ones that you're wearing today. Kind of a pretty thick one with a little knob on it so you could tie things to it and put it on the subject's eye. Okay? And then what he did is he attached, so we've got a subject with a contact lens on one eye, the other eye is normal. No eye, no contact lens. Sorry. The eye is still there, really, the eye is still there. He attaches a rod to the contact lens to restrain the eye, right? So you've now lost control of your eye, Dave Robinson is controlling your eye. And then he covers that eye and asks the other subject to fix different static positions with the seeing eye. Okay, so the seeing eye is the one without the contact lens and the rod, right? And what he does then is he measures the force that's being placed on sort of the resistance. There's basically a torque generated that he can measure, right, against this rod, and see how much force is generated when the other eye is in each position. So what's the one assumption in this type of experiment? The subject doesn't blink. Well, I mean, the subject might blink, but yeah, he would be doing the recording while, I guess, the subject's not generating blinking movements and making sure the eye was really looking.
That the eyes move together.
That the eyes move together, right? So the idea is you'd have someone looking out, far enough that we would assume that the command going to all the motor neuron pools is conjugate, right? And most of the eye movements we generate are conjugated. I'm looking around the room, my eyes are really moving around like windshield wipers. So the one assumption in this is the programming of the muscles is trying to generate conjugate eye movements. So when this eye is looking over here and you're holding this eye fixed, this eye is really trying to go over here too. Okay? And when he does that, what he sees are these movements, right? So he's measuring basically force as a function of time, and you can see this there's a baseline force, and then there's this V term with increasing eye position. Eccentric, the eye is generating more force against this restraint, right? And what you can do is now you can measure not in this transient period when you're initially making the saccade, but when you're trying to hold the eye steady, right? Okay, so that's a good way of estimating that sort of that V term. Okay, so then he comes up with another experiment, right? And so the subject still has this suction cup lens on their eye, right? And this time, instead of putting a rod on it, he's going to tie a thread around it, right, around the little holder it has on it, cover this eye again, and then ask the subject with the seeing eye, this time is just stare straight ahead. Okay? And then what he's going to do is take the little string and pull it to the side and then let go. Right? So again, the assumption is, so the idea is you're staring straight ahead, Dave Robinson is now controlling this eye, pulls it over, and it's zooming back. So again, the assumption is that the eye movement command is conjugate, right? So there's really no command to move this eye. Dave's controlling it. But this eye's going to want to go back to its natural resting place, right? Because this eye's staring straight ahead, and that's the command that this eye is getting. So this is a way of getting a sense of sort of this elasticity, right? You pull the eye over, and then it goes back. And also maybe the viscosity. Maybe it's springing back with some dynamics that are more consistent with this first order differential equation than just Hooke's law. It's not going to spring back like the law's right, but it takes some time to come back over. So that's what you see here. You see basically when he pulls, you get, depending on how far over he pulls, you get a bigger and bigger deviation, and then the eye comes back. What's a little confusing here is he's zeroed them all out here rather than here. In terms of position, you're all going back to the same place, right? So this is more of a delta E than an E, right? If we plot this in terms of absolute eye orbital position, all these traces would line up at the end, right? Because it's all going back to center. Okay. So what he found is you could fit this sort of return of the eye back to the center with a set, basically this first order differential equation. It's got two terms, a B and a C term, and if you took the difference of these, which is effectively the time constant, right, if you solve that equation, he came up with about 200 milliseconds. Okay, one last experiment, because the subject's still there, still wants the letter, right? So what he did, he tested, so far what we've seen so far is consistent with both a elasticity and viscosity based on that last equation and fitting that equation. But how about inertia term? So what he did is he actually, again, took this contact lens, this time attached a ball and socket joint to it, attached it to a little cart on a frictionless sled. I bet none of you guys thought of that. Which he then weighted so it had 100 times the normal inertia of the eye, and asked the subject to make sequence. At least I can see people are paying attention today, right? So what he found, and this is really shocking to people. People kept trying to find other ways to use experiments. He got it right. That the eye actually still lands in the right place, so inertia is not a really important problem for this. The term is pretty negligible. So we don't have to worry about it. So that's a good thing. Makes the math simpler. So the mechanics of the eye are then pretty much described by this simple viscoelasticity, which is a first-order relationship between force and eye position. Okay. So summary of the experimental results, we came up with this formulation and said that the eye plant is dominated by this viscoelasticity, and that the combination of these two elements, I gave you some intuition early on, right, of a spring and this viscous, like syringe-like element, are often considered a simplified muscle model. And again, if the motor neuron firing rate is proportional to the actual force that's generated by the muscles, which it seems to be, as you'll see, then this relationship can describe a motor neuron firing rate and eye movement. Okay. So now what I'm going to do is go through a similar sort of series of experiments to see what the motor neurons actually do, and try to get a better sense of how they're behaving during these kinds of eye movements. So here we have, again, 3 experiments. So the first is the monkey looking straight ahead. And I should note the way that the eye movements are recorded in this experiment was designed also by Dave Robinson. It's still commonly used in laboratories. Eye tracking is finally really at the level, I think, where people are starting to use eye tracking. But the resolution of this method is really incredible. The idea is you sit a subject in a big magnetic field coils that are both horizontal and vertical magnetic fields are generated. You implant either in human subjects, you can put a coil on a contact lens, or in animals, you can implant the coils under the conjunctiva. As the coil cuts through the magnetic field, it induces a current in the coil. And by either putting the fields in quadrature or changing the frequency between the two fields, you can actually decode how much the eye moves horizontally versus vertically. You can also do it in 3 dimensions, you get a torsion. And Dave came up with that too. So these monkeys, he has very precise eye movement recording, like the first of the that people were able to do. He has the monkey look straight ahead and records the constant firing rate of the neuron when the monkey is staring straight ahead. And he's going to call that the resting discharge. We're going to call that R naught here. So the firing rate when the monkey looks straight ahead is R naught. And on average for motor neurons, it's about 100 spikes per second, but it varies quite a bit. So experiment 2 is we're going to have the monkey kind of like the person was doing, but we're not going to hold the monkey's eye and move his eye back and forth to look at different places. And let's say this is when the monkey looks up, the neuron turns off. When the monkey looks down, the neuron turns on. So this is an inferior oblique motor neuron. Okay, that is recording, so that would be the third nucleus. And what you can see here, these are all little action potential down or spikes down here. And what you can do is say, okay, I'm just going to look at the times where the monkey's not making saccade, but where it's fixating, compute the average firing rate for those different eye positions. So you compute one for this upward movement, one for this downward, not movement, one for this upward position, this upward position, this downward position, this very downward position, etc. Right? So you could compute one value, one firing rate for each of those different eye positions, average over the interval. And then what you can do is plot that. So you have average eye position during apex of fixation versus average firing rate. You get these nice linear plots. They're really great, like one of the most linear things that you can find in brain. So then we have this new simple equation where we have that R naught, which was the resting discharge, plus this KE term, where K is just the slope, right, of this relationship. Okay? And on average, this K would be about 5. Then finally what we can do, because we also know that velocity is important in the system based on the mechanical analysis, so what happens when the eye is actually moving. So here what he did is a smooth pursuit experiment where he had the monkey looking at a sinusoidal stimulus going back and forth and tracking that. So this would be the eye velocity as the animal's tracking the stimulus. And then when you blow up this little bit of it, you say, okay, let's take one eye position, but when the eye is moving at different velocities, so we hold eye position constant, and we see just the effect of eye velocity. Okay? So for example, here it's kind of extreme. In one case, the velocity is going upward. In the other case, it's going downward, but the eye position is the same, right? Everything crossing that blue line would be the same eye position. And if you do that, you get another relationship. So this would be basically fire rate versus eye velocity, holding eye position constant. And the slope of this curve would then give you the relationship between eye velocity and fire rate. Okay? So we have fire rate equals, again, some resting discharge, which would be your intercept, plus R times ED ET, first derivative. So if we put this all together, right, we have firing rate at rest, we have the eye position, the eye velocity sensitivity, we end up with this summary equation here, which is firing rate equals some resting discharge plus R times eye position plus K times eye position plus R times eye velocity. You can put these three together here, and basically the way it's generally represented is that change in firing equals some KE plus R dot. And that's a pretty good representation of firing rate of motor neurons over many different types of behaviors. So just to put together what I told you, right, is we started with this really mechanical approach that Dave Robinson came up with, really in a very intuitive way, probing how do your muscles constrain your eye movements and the soft tissues in your orbit, what do you need to overcome, what existing forces do you need to overcome when you're generating that command to move the eye muscles. And then we also came up with a description of the motor neurons. We found that the eye movement, the appetite is viscoelastic. This has a viscous elastic force that's shared by this elasticity KL and viscosity R dl dt. The good news is the motor neuron equation that we described, right, actually has the same form. So this implies actually that the relationship between muscle force and firing rate is indeed linear, right? Because we're looking at motor neurons, not actual force, but we can actually, the form of the equation is pretty comparable. Okay, so what are the implications of that? So the first thing to think about is if you want to drive the saccadic eye movement, how would you do it? So the question is, what would you expect the motor neurons to have to do? So you could think of a case where the input to the motor neurons is just this step input, right? Or the fire rate of the motor neurons is just this step input to the muscles. And the question is, if that was what the motor neurons were driving, if that was their actual response in terms of firing rate, what would actually happen to the eye? And based on what we know, right, this is the equation, we can then solve that equation, right? It's basically a first order differential equation, so the solution is going to have something of this form. And to find its time constant, what we can do is set T to TE, and that basically tells us that we should be maybe 63% of the way there for our time constant, which is basically going to be the ratio of R over K, and on average that's about 200 milliseconds. So what that means is if you just use this as an input, your eye movements would be exponentially approaching their target with a time constant of 200 milliseconds. That would not be very good for us, right? Because we make saccadic eye movements really quickly, and they're not creeping to their final trajectory. So they would be too slow, and generally we make even really big saccades within 100 milliseconds. So what does the brain do? And I'm sure you guys can probably guess, and there were some clues in what I already showed you, right? Is that to make saccades, what the brain does is generate something called a pulse step. So the idea is that the pulse is something that kicks the eye in the direction it needs to go. So it's an extra burst in the firing rate. So if you look back at some of the examples I showed you for that inferior rectus neuron, what you'll see there are actually bursts that occur during the saccade and then a sustained firing rate once the eye is in its new position. So that burst is considered the pulse and helps to make the saccade, get the eye where it needs to go in a faster amount of time and overcome that viscous drag that we talked about. And neurons that drive that burst are called burst neurons, and they're in the PPRF, and I'll show you where those are in a slide in a minute. And then once your eye is at its new position, what the brain needs to do is generate a step to keep it there, because we know that the eye actually wants to go back to center, right? So in order to keep it eccentric, it requires a force, and that force is generated by the motor neurons. So you need a tonic sustained response to keep the eye at the new location. Okay. So this is what's shown here, the idea that this is the pulse and the step in terms of firing rate, and if you just look at it in terms of actual spikes, right? The pulse is a very fast firing part of the discharge of the motor neuron, and then you have this sustained but less intense static response that keeps the eye in the new position. Okay. So this is interesting, but is it useful to think about pulses and bursts and steps and sustained responses? Do these map onto anything in the brain? And what Dave came up with was this idea, Dave Robinson, that the pulse is produced by neurons that actually sit right below the sixth nucleus, the abducents, that just burst when you generate a saccade. They actually don't fire when you're fixated. And these are called burst neurons. There are two circuits. There's one that controls horizontal eye movements. We'll focus on those. Those are PPRF neurons. But there's also RI MLF neurons that are up in the mesencephalon. So if you look back at that little bit of histology I showed you, or that cut away the brain, the structures up in the midbrain that are colored in green, those are actually part of the vertical and torsional system. And then the structures back in the trons are the horizontal system. So I'll explain that a little bit more. And the hypothesis is that you take that burst signal, that pulse, and you integrate it, or your brain does, to create the step. And I'll show you the evidence for that in a minute. Okay. So again, I already showed you this sagittal section. What you can see again in red are the motor nuclei. So what's shown here up here are the rostral IMLF. That's the burst for the torsion and vertical system. And then the PPRF, which has the burst neurons for the horizontal system, sits down here in the pons. Okay. And then there's a second nucleus in both of those systems that actually work like what are called neural integrators. So the idea is they take that burst and they integrate it through reciprocal loops within each structure to keep sort of a memory of that burst. And that basically keeps the sustained signal that keeps your eye then at that constant position. So for the horizontal system, it's called the nucleus prepositus, and it's been very well studied. It's a great model system for understanding neural integration. And then up here is the interstitial nucleus cajal in the vertical and torsional system. And I just want to go back here to make the point. So the reason people think of it as a neural integrator, right, is you can think of the pulse, right, or the burst part of the motor neuron response here is looking a lot like eye velocity, right? And then you can think of this step part as looking a lot like eye position. So the idea is if you have a group of cells that are encoding eye velocity, which would be these burst neurons, it's effectively a neural integration. You have a second group of cells that are representing the integration of that velocity-related input and representing position, so that they're contributing this step part, which looks like position. So what Dave did is he actually located this nucleus that's just next to the sixth nucleus called the nucleus prepositus. And what he did is he made lesions of the nucleus prepositus. So this just shows a normal monkey looking around. You can see this is right and left, right being up and left being down, or down and up. And the monkey's just looking around. You can see normal saccades and normal fixations. And then what he did is he injected lidocaine in the nucleus prepositus and watched what happens. And you can see there's really no change in the vertical eye movements, right? The monkey's still scanning the environment. But what you see right away is something really weird is going on with the horizontal eye movements, right? So the monkey can make the saccade, because the burst neurons of the PPRF are still there. But once he's made the saccade, the prepositus cells aren't there to keep that static signal coming. There's nothing to keep the eye, you need a force to keep the eye centered, so the eye just drifts back. Right? So the idea again is he's basically activated the nucleus prepositus. That's where the neural integrator is. The burst neurons are still driving the saccade, the burst neurons in the PPRF and the horizontal system. So you get basically this drift because once the monkey's made his eye movement, there's nothing there to keep the eye over, off the center, and the eye just drifts back to the same time constant we saw in Dave Robinson's original experiments in humans. So this is a little model of what that looks like. This is the burst neurons in the PPRF just fire during the saccade, right, during the velocity part. They project directly to the motor neurons. We know that's true. You can't move the eye. And then we also know that the nucleus prepositus gets direct input from the burst neurons. And then within nucleus prepositus, you basically have reciprocal reciprocal connectivity between neurons, which both basically forms a positive feedback loop with some decay, so it doesn't blow up. Right? So the gain has to be less than 1. The time constant of this integration is actually pretty high. It's on the order of like 26 seconds, so it's hard for us to see decay unless you have a patient. And it's actually a way of knowing that you have a patient with some sort of problem in the brainstem that might be in this area was they would have something called a gaze-holding nystagmus, which would just be if whenever they try to hold their eye eccentric, it would drift back to 0. So this is actually a really good marker for certain sorts of brainstem pathology. Okay? So again, the idea is you have a burst that drives a saccade, right? But the burst also goes into this nucleus prepositus, and then even though the burst is over, it's going to basically, there's since you have recurrent feedback within the nucleus prepositus, it's going to basically, it's a form of memory, right? So it goes around in this little network. And that creates this position signal, so effectively neural integration. Okay, so what you can see here, and this is the superior colliculus that I mentioned. The superior colliculus gets input from all the different cortical areas I described. So it's sort of think of it being a hub. Whether you decide to look at something or not, you decide to stay looking at what you're interested in or move to something else. This seems to be like the final deciding point. So it gets input from posterior parietal cortex, frontal cortex. It's a very interesting place to do experiments. There's a nice map of visual and motor eye movements across this. It's organized in a very didactic way. The red part is the fixation zone. If you stimulate the red part of this structure, the eyes will not move. And the caudal part, as you go more and more caudal, you stimulate to get bigger and bigger saccades along the midline, the horizontal. If you go off the midline, you have vertical components. So I'll stop there because I think you guys didn't hear anything about the colliculus. Is that true? Yeah? Okay. So I mean, I think it's very interesting. So I'll start with a couple slides about that on Wednesday, and then I'll talk about this.
Do I not